We are ready to continue. We move to TCP. As we have seen already, TCP solves the problem of losses as much as it can be solved, once for all, which means the programmer doesn't need to worry about repairing packet losses. Of course, TCP does only what is possible if the physical link between the computer and the rest of the world, for example, is broken, packets don't reach, and they cannot be repaired. So as a programmer, you must still be ready to handle cases like this, right? Which is essentially you've lost total connection. But if individual losses occur, then you don't need to worry about it. In addition, TCP guarantees lossless delivery, this was said. In addition, it guarantees that the data is delivered in sequence. Right. What does it mean, in sequence? That means that if an application sends data, for example, by doing a series of n write calls into a TCP socket, some of them are lost, some of them will be repaired after some delay, for example. TCP will deliver the things only in exactly the order that they were delivered. So if you send byte number 1, 2, and 3, number 2 is lost, and it takes some time to repair it, but number 3 has arrived at the destination. Number 3 will not be delivered to the application before the loss of 2 is repaired. That's the in-sequence delivery. Why is that done? Well, it's a bit like the MAC layer. There were good reasons 50 years ago that may be a bit less good today. TCP is really the same as the TCP that was invented in 1974 when the TCP-IP was created. At that time, the idea was to simulate with TCP what you have when you have a direct physical link. Remember, many computers at that time were connected only through local area networks over a cable. And over a cable, you have in-sequence delivery of things, of course, and very little loss. And TCP was doing the same over a network. So it's sometimes it's called a virtual circuit or a virtual wire. We will see that today, perhaps it's not always a good idea. For example, if you transmit a web page that has lots of objects embedded, scripts, images, etc., TCP will insist on delivering the objects if you transfer the web page over a single TCP connection. And if one of the objects is missing, a small image, that's a logo, for example, that you really don't care about it, but the script, for example, will not execute before the logo has arrived here. So if you do things in a naive way, think that can happen. How does it work? Well, it uses a very simple-minded approach where you number the data, and if something is missing, you see that because the sequence of numbers tell you that there is a gap. So the acknowledgements will indicate whether some data has effectively actually been received, and if not, through some loss detection mechanism, they will be retransmitted. So loss detection, we've seen already one mechanism with the stop-and-go protocol. It's a timeout. TCP does this, plus a number of other things that we will also discover. So here is a small illustration of a very simple case. Here I have a machine A that is sending data to a machine B over TCP, and the data is numbered. Now, one of the specificities of TCP is that because TCP thinks of itself as doing a virtual wire or a virtual circuit service, it numbers the data by byte. The unit of data for TCP is really the byte. So the sequence numbers here in the data, for example, here I have a packet of 500 bytes. So there is somewhere in the TCP header the information that the numbers are those that are given here. So one of the conventions in TCP and Wireshark is that the last one is always excluded. So when we say that, it means 8500. So the 85001 is the next sequence number that you expect. That's not included. But that means the difference, which is exactly 500, is the size of the TCP segment here. So those 500 bytes are sent. The job of TCP at the receiver side is to acknowledge. So it will send an acknowledgement, And the acknowledgement field, for some other reasons, is cumulative. So in the TCP header, there's a field called acknowledgement, and it's cumulative, means if I acknowledge this number, it means I am acknowledging everything since the beginning of the connection to this number. Here it's the first packet, so it means this packet was acknowledged. Then the source continues sending packets, but two following packets are lost in the network, and the third reaches here. When B receives this data, B will acknowledge, so B always acknowledges something, and what it can acknowledge is only the same number as before, because the acknowledgement is cumulative, and the logic of TCP is to deliver things in sequence, so the acknowledgement field acknowledges all the data that have been received in sequence. So here in this case, we see that there is 500 bytes of data that has been received, and this is not in the acknowledgement information. We'll see it will be somewhere else, but it is not in this acknowledgement information here. One mechanism for detecting losses is timeout. For example, if this happens here, this packet was lost, like in the stop-and-go protocol. We wait for some time, but hopefully is well computed. It's larger than the round-trip time, but not too large either. And then when it fires, it means I've received no acknowledgement for that. I suspect it's lost, so I will transmit it again. Observe here that this acknowledgement is lost, but this acknowledgement did not contain much information anyhow. But this can always happen. When you don't receive an acknowledgement, you don't know whether it's because it's the data that is lost or the acknowledgement that is lost. So TCP must be able to live with that. In particular, if you send twice a packet, that should not create a problem. You can send twice a packet because, for example, this packet is sent, but the acknowledgement is lost. So A would be not detect that it is lost. B has received it, so A will send it again. So a TCP receiver must always look at the sequence numbers, and since the sequence number are per byte, this is very convenient. If you receive something that has the same sequence number, you know it's a duplicate, and you throw it away. So here, the packet that was sent at number 3 is sent again at time 8, here. And now we see that the logic of TCP is to deliver data in sequence. So here, all the data that had been received could be sent, but at this point, the packet number 5 cannot be delivered, because if I would deliver it to the application, I would violate the in-sequence delivery. So I will not deliver it. It's kept, of course. It's not thrown away, of course. It's kept in the buffer of the operating system, but it's not delivered. When the second packet arrives here, then we can deliver this second packet, so the bytes that are in this packet, which will be acknowledged here. So we see 9,000, and so an acknowledgement is sent. Now the acknowledgement is increasing the value to 9,001, which is corresponding to the first 2 packets that are now being received. The third packet will also be retransmitted at some point, and when the third packet is received, the third packet, the data that's in the third packet can be delivered to the application, and also the data that was at the packet at line 5 can also now be delivered. So we can deliver this block of 2 packets. This is how the in-sequence delivery, the sequence numbering, how they work together. Of course, the ACK field is cumulative, which is the idea they had in '74. And of course, it's not a good idea to only do this, because here we don't give the information back to the source that the packet at line 5 has been received. So probably the source will retransmit it sometime. So soon after, the designers of TCP invented the SAC, selective acknowledgement field, which seems obvious by today's view of things, but took some time to happen. So in a TCP control information, there is an ACK and SAC, one or several SAC blocks. And the semantic is the ACK indicates that everything up to this number has been received in sequence. And the SAC gives the information on additional blocks of information that are with gaps and that have been received. So this information will indicate that the packet at line 5 has been received, and this will prevent the source A from resending it. So this is how the basic operation of TCP works. Of course, because of this in-sequence delivery, there must be a receiver on the destination side, and this receiver contains all the packets that have been received and are out of order. For example, at this point in time, we had one packet in the socket receive buffer that is not accessible by the application. It is present, but it's not accessible. So if the application does a read for first read, it will receive this one. If it does a next read, it will get the response. There is nothing to read. The buffer is empty because the usable part of the buffer is truly empty. Of course, here things will be different when it's received. So that's the basic stuff. Now, if we do this, we immediately uncover a number of problems that occur with that. One of the problems is, for example, the size of the receiving buffer. So imagine a scenario like this, where you send a packet. To make the story simpler here, I put packet numbers, but remember TCP has sequence number. By the way, there are other protocols at TCP that do similar things that may use packet numbers, but let's ignore that. So packet 0 is sent and lost. The source continues and sends P1 and P2. Then because of the in-sequence delivery, P1 and P2 will be stored in the buffer. And the source continues to send. And assume bad luck, whenever P0 is transmitted, is lost again. Of course, this will not happen very often, but since we do lots of things in networks, we send millions of packets, even rare events will occur once in a while. So it will occur, a scenario like this will occur if you wait long enough on a given server, and what will happen is that the receive buffer will grow in size here. So a server that has a buffer that grows, that will cause a problem. There will be buffer overflow, which would be stupid because that means we might discard packets where if packet Pn+1 comes, for example, or an n+2, and the buffer is full, it will be discarded at the destination, which is the most stupid thing to do. I mean, you send a packet through all the jungle of the internet, and at the destination, in a perfectly operational server, you throw it away because the server buffer is full. So that's something you want to avoid from happening. TCP avoids this by using what is called the sliding window. So the sliding window says essentially that there is a maximum number of packets that can be non-acknowledged, that can be on the fly. For example, here, the window size is 4 packets, and every packet is 1,000 bytes. Of course, as you can anticipate, in TCP, everything is counted, almost everything is counted in bytes, so the window size is in bytes as well. But to simplify the story, every packet is 1,000 bytes, and the window size is 4. That means here that if we look at a scenario like this, I have a source that has all this series of packets to send. It can send 0, 1, 2, 3, so it sends 0. As soon as it receives an acknowledgement for the packet labeled 0, then it's able to send 1, 2, 3, 4. Because it is always able to send up to 4 non-acknowledged packets, packets that are waiting for confirmation here. So when packet 0 is sent and not yet acknowledged, I can send 1, 2, 3, but I cannot send 4, for example. But as soon as the acknowledgement comes, I can send. Of course, the source will also have its own constraints. It's not able to send packet instantly. It needs to process them, so things don't occur instantly. It takes some time. So here I'm assuming the 3 packets are sent in this way. Same thing for acknowledgements. Acknowledgements are processed by the destination. That may take some time to process them. They're transmitted over the network. That may also take some time to transmit the packet, so they may arrive late. Here, when the packet just before A=1 arrives, the source was able to, the window did not move, so the source was able to send 3 and 4 that is sent here. But just after sending the 4, the source would not have been able to send anything. Fortunately, acknowledgement 1 came, so it can send everything. But here we see that at this point in time, the window did not move, and all the packets in the window are sent, which means the source is blocked. The source will stop sending because it has sent already 4 packets. They are not yet acknowledged. So the source thinks those packets might be sitting in the destination buffer and not yet processed. So I don't want to overflow the buffer with the syndrome that we saw in the previous slide. So this is how the the sliding window works. So let's test your understanding on this little quiz. So here we have a small diagram with a source that sends 4 packets. The first one is lost and it's acknowledged. So we have received the acknowledge of not of the first one that is lost, but the following packet is received and acknowledged. So I'm using a syntax that's similar to TCP. And the packet s equal 2 similarly is received and acknowledged. S equal 3 also is received and acknowledged. And when all of this happens, what is the sender allowed to do? I close the poll. And the majority says B, which is exactly correct. That's the window size is 4. You have sent this one is not yet acknowledged. So I can send those 4 packets, but those 3 ones have been sent, so I cannot send new packets. I can resend this one, but I cannot send new packets. So this source is blocked until it detects the loss and repairs it. So TCP uses a sliding window to avoid overflowing the resequencing buffer of the destination. But that's not enough, because the resequencing buffer, which is in fact the socket buffer at the destination, may have problems because of repeated losses, like we've seen, but it may have problems from the other end here. It may have problems on the network side, but it may have problems on the application side. For example, if I have an application that's very slow, I have here a perfectly working TCP connections with no losses, so packets are sent, acknowledgements are sent, but the application is busy. The server is busy. That happens all the time, of course. It's very hard to dimension the pace of a server to exactly the pace at which the source is sending. We do that in industrial networks. It's a completely different setting, where if we know I have a machine that sends 1 packet every millisecond, then I create a receiver that receives also every millisecond, and then I can compute how many packets it can handle. If you do a web server, you have no idea how many requests you will receive. You're limited by the network. But if you have a complex logic in your web application, if you need to access a database, for example, if you have complicated calculations to do, you don't know how much time the server will run. So that can happen, as I said, by poor design or simply bad luck or congestion. So what will happen? Well, the buffer overflows, and then we are back with the problem of having stupid losses. It's better to say to the sources, don't send to me because I'm congested, instead of allowing the sources to send to me and congest me, because the sources, we use resources of the sources, of the network, also of the data center, of the network of the data center, etc. So that's the problem. The difficult thing is to detect the problem. Once we've detected the problem, the solution is obvious. Well, the solution is to adapt the size of the window. Here, I presumably had a large or a window that allowed the sender to send. Sorry, one way to do would be to prevent the destination from sending acknowledgements. We could say if the application has not consumed all the data, I don't ACK them to the source. That would work in the sense that the source would stop sending after some time. But if we do this, there are other side effects that are negative, which is that the source uses the ACK to know that the packets have been received correctly. So absence of ACK will be translated by the source into the need to retransmit, which will make the congestion even worse. So that's not a viable solution. The viable solution, the solution that is used, consists in using the fact that the window is an indirect control of the rate at which an application is sending. If you give to a computer a window of 1 packet, or 100 bytes, let's say, that means that it can, in the very best case, it can send 1 packet every round-trip time, 100 bytes, right? Every round-trip time, which is very small, probably. If you give a window of 10,000 packets, or 1 million bytes, then you allow this computer to send much more. So indirectly, the window size, when there's no loss, controls the throughput of the sending application. We will see how this is used for congestion control. This is used for flow control. We can reduce the rate at which the application is sending by reducing the window size. So TCP uses a sliding window, and TCP constantly adjusts the sliding window by the receiver. It is the receiver that will, in fact, advertise a sliding window that is exactly equal to the size, the available size of its resequencing buffer. For example, if we take this case revisited, we see that there will be acknowledgement fields that come, but also window size. Here I'm giving a window size in packets to simplify the story. And we will see that at some point, for example, when the congestion occurs and the socket buffer is completely saturated, the destination will send even a window of 0, which is a stop signal. That means when you receive a window of 0, you don't send, which is a good thing. This destination was unable to consume all the data I, as a source, have sent. There's no point in me sending more. First, wait until the destination has received it. Of course, when you send a stop signal, there will be a few nasty side effects that may occur that you need to catch. What if the stop signal is cleared here because I send another window of 4 now? So we see here this source could not send, now it can send again. What if this ACK is lost? Right? Because the ACKs are also TCP packets, they can be lost. So if this ACK is lost, the source is blocked and is blocked forever. Now the source is blocked, so it doesn't send anything. So this guy will also not send any ACK because it's seasoned. So we have a deadlock. So of course, you need to do something against the deadlock. So the TCP standard says when you send a window equals 0, the effect of the window equal to 0 is valid only for a small amount of time. So if nothing else happens, after some time, there will be a probe packet that will be sent by the source will be able to always to send at least 1 byte. So even if you say 0, you can always send 1 after some time. And by sending this 1 byte, that will trigger more ACKs to come. And if it was due to a loss, the new ACKs will have a non-zero window that will unblock you. Why would we have a scenario like this? Why would the window change all the time? Well, if we uncover what happens on the receiver side, that might be the reason. So we see that the receiver has received packets, and the packets that are in dark blue are the ones that are ACKed but not yet consumed by the application here. And the light blue is the free socket buffer here. And we see that the rate at which the source is sending is, of course, never exactly the same as the rate at which the application is consuming the data here. Here we see that the application has consumed all the data that has arrived. Therefore, we send a window of 4, and we might even send, when the window size changes, that may be a reason to send 2 different ACKs. When this packet has arrived, I ACK it, and I give a window of 2 because there's only space for 2 here. But when the window changes, because the application has read, TCP might and will often decide to send an ACK. Here we dive into the zillions of optimizations that exist in TCP, and not all versions of TCP are done the same way. TCP is free to send an ACK whenever it thinks it's a good idea to send it. Here, in contrast, we see that the application did not read all the data that has arrived, so a window of 0 was sent here. Then the application read them, and then a new window was sent here. So this is what every TCP sender and receiver will do. Now, if we put things together, we don't have one-way communication, but two-way communications. That means the 2 sides of a TCP connection are both sender and receiver, which means that the TCP packet contains both an ACK and a sequence number in its TCP header, which is illustrated here. There are 2 spaces of sequence number, the space of sequence number of A and the space of sequence numbers of B. The sequence numbers sent in the TCP packet are in the space of A, and the ACKs sent by A are in the space of B. So this message here means A is sending a packet of 500 bytes that are sequence numbers in this range, and is ACKing packet 101 of the packet sent by B, and is advertising a window of 6,000. So those fields are when A acts as a receiver, which means that B can send at most a window of 6,000 bytes. For example, B sends 100 bytes. A acks them. We see here that the ACK 201 works. The window has changed. 1 packet is lost, and this will be visible in the ACKs that are changed. Here I have a SAC field like we saw before, but the new thing is that we have both A and B that are intertwined here. There is not the concept of a sender and a receiver. Both sides are both sending and receiving. Small quiz about the indirect control of the rate of an application here. I'm assuming I have a sender like TCP that has a window size that uses a sliding window. And I call RTT the time it takes between sending the first bit of a packet until receiving the last bit of the ACK for this packet. And assuming every packet receives 1 ACK, right? And I'm assuming the optimistic case where there is no loss. Right. You recognize with W equal 1 the stop and go protocol. But now I have a general W. What is the throughput that can be reached, or more precisely, if we want to have a throughput equal to C, which is the capacity that we would have if we would not have any other limitations, what is the window size we need to reach that throughput? I close the poll. It's a more tricky question. The majority says A, which is the correct answer. Perhaps one simple way to visualize why is to look at what happens when the condition is true, when the window is larger than the throughput, the maximum, the throughput that's reachable if we have no constraints, so multiplied by the RTT. Then we have a pipeline where we see that we always receive acknowledgements and we are able to send at a rate of C here. In contrast, if we are below, then we'll have a behavior that's more like the stop and go protocol, where we're forced to stop. We cannot send at a rate C. We are forced to send 2 packets, for example, here. I need to wait. This is what happens when the RTT is long enough here. So this illustrates concretely what I said before, that the rate of a TCP source is controlled by the window size, at least in the good case where there is a no loss here. If I want, another way to put that is if I want to give to this source a rate of C bits per second, if I know the RTT, which TCP does, TCP measures the round trip time, then I need to give it a window W. This justifies why TCP is also used for controlling the rates of sources in the internet, which will be the topic of the module on congestion control in a few more weeks. Before getting there, let us see other bells and whistles about TCP, and in particular, how we use it with sockets. TCP is more complex to use than UDP. In particular, it requires that synchronization is performed before transmitting the data. In particular, we need to know what is the initial sequence number. We could start with 0, but that would have a number of problems. So we need to make sure that everything is clean, that for the sliding window to operate, we must be sure that we start with a clean window that has no pending acknowledgement. This is why TCP starts with what is called a handshake. So this is a time and space diagram here. Time is flowing vertically, and now I'm showing the packet sent instantly. Before using TCP, the client side must do what is called a connection opening handshake, called a SYN packet. Why SYN? Because it's a TCP packet that is used for synchronizing the states of the two ends, and it contains 1 bit in the TCP header, which is called a SYN bit, which is set to 1. So this packet is sent. It must be acknowledged, because like any packet, it can be lost. So if it's lost, it will be retransmitted, and all the things as usual. And when this happens, both A is sure that B knows the sequence number space of A, therefore it can start sending acknowledgements. There is also a reverse handshake, because TCP connections are always two-way. So at the same time that A advertises its sequence number, B will also advertise its sequence number, and thus must be sent by A. Typical applications will wait for those 3 packets to have been successfully received before sending the data. So that means if A has 1 byte of data to send, it must send a packet, wait for the acknowledgement, send another packet, and only then send the first byte here. So there is an overhead in sending TCP. This is why DNS clients don't use TCP. If you have a simple request to send that fits in 1 packet, you don't want first to send 2 packets and wait for a 3rd one to come before sending your request here. But if you do what is called a TCP zone transfer, that means if a DNS server copies the entire database of another DNS server, there's a standard protocol for that, they will do it over a TCP connection. It's not because DNS is a fanatic of UDP. So if you have a single message to send, short message, you use UDP. And that's the reason, because using TCP would cost you at least 3 messages. The connections also need to be closed, because a TCP connection uses resources of the operating system. And if you don't use it, it's a good idea to free it. So you can free it by sending a FIN packet, which means terminate the connection. It's called a graceful termination. And this is a bit complicated because it can be terminated in both directions. Terminating the connection means there is nothing else to ACK after that, and any read that will be done by the TCP's receiver here will have a message indicating that the connection is closed, which means that there is nothing else to read, which is an end of file signal that is sent. So the only structure information that the TCP connection sends is whether it's finished or not. In contrast to UDP, UDP sends you one message. If I send 3 messages in sequence with UDP, I will have the limits of the 3 messages that are sent. With TCP, the only thing I know is it's finished. So in TCP, essentially, I always send 1 message, and the only information that TCP gives is when it's over. Now, they can be transferred in both directions, so you may have weird cases where a connection is closed in one direction because all the data has been sent and acknowledged, but data in the reverse path has not been entirely acknowledged, so it's open in the reverse direction. So you can have all those cases that happen here. And those boxes here mean the state of the TCP connection. Because of its complexity, the TCP header is usually a bit more than 20 bytes. The TCP header contains the source and destination ports. The source ports are 16 bits, as we know, so that's already 32 bits. The sequence number and the ACK number that are 32-bit each. Typically, it will also have SAC blocks that will be typically several times 4 bytes. And also a number of other things like the flags that I've mentioned before that indicate whether it's a SYN packet or not a SYN packet, for example here, or a FIN packet. So SYN packet means the only first packet that we send in either direction to open the connection. Here. When we use sockets, on the client side is not very different from UDP, except we still need to do a connect. So a TCP connection, a TCP socket is always connected. Connected means it is for a given specific remote system. This socket here, this TCP socket, of course you must do the binding as usual like UDP to the port number. It can be done implicitly. But in addition, you need to connect to the remote end. Binding is to the local port and to the local address. But a TCP connection is always for a given destination. A UDP socket is typically not, although a UDP socket can be connected, but that's another story. So before sending any data, we must do the connect. Connect takes at least 2 arguments, which are the IP destination address of the destination and the port number. So this is in symbolic form what I wrote here. And the effect of this is to do the 3-way handshake, to send those 3, to have those 3 packets exchanged. When we do connect, the operating system sends a SYN packet, waits for the SYN ACK. If the SYN ACK doesn't come and times out, send the SYN again, etc., until the SYN ACK comes, and then sends the ACK of the SYN ACK. On the other side, if the SYN ACK is an ACK of the SYN, but also a SYN, so the same thing will happen. The SYN ACK is sent. If the ACK doesn't come after some time, it is repeated until the ACK arrives here. So that's the client side. After the connect occurred, then you can send data here. On the server side, you have the same thing, except on the server side, you typically bind explicitly. So here I gave the port number. And then you do typically something else, which is called listen. So the listen call means that I start a queue and I specify the parameters of the queue. It can be done implicitly, but in this form, it's done explicitly for the SYN packets here. So in TCP, in a TCP socket, there's a different queue for the SYN packets and for the data packets here. And once this is done, you can, the SYN listen means I'm open, I start the queue of receiving SYN packets, and then I can read one of the SYN packets, which means I can see whether there is a connection opening request that has arrived in my listen queue. And if I issue this call, which is the accept call, that means I create one connection from one of the pending connection requests. So we create the connection. At this point, the connection is open, and then we can exchange data. We can exchange data, except there is a special twist here in TCP. On the server side, I put the things in pink here, because when we do an accept, the accept returns another socket. So here, the server uses one socket for handling the connection request. As soon as one connection request is accepted, the operating system forks another socket, which is bound to the same port and the same address, but is now connected to a remote destination. And this is illustrated by the pink socket here. So the receiving data, now one sends some data. When I receive data, I receive it on the other socket that is created here. So here in this figure, there are two sockets. The first one is non-connected, because that's a socket that's used only to receive connection requests. So we may receive them from anybody. The other one is connected. The other one is connected to this system here, to the client. So I can receive data only from a given client here. When I receive the data, I don't need to do a receive from, because the whom I am receiving for, I have all the information from the accept here. So similarly, when I send, I don't need to say send to, I simply say send, because whom I am sending to, the information has been cached when I did the connect. So sending, receiving from a TCP socket is like writing or reading from a file. This is exactly, in fact, you can use read and write also, with some, in C at least, which has exactly the same semantic, not only from the viewpoint of the syntax, but it's like also reading from a file. When you read from a file, you read from a sequential file a certain number of bytes. That's exactly what you do from a TCP connection. In fact, the mental model of a TCP connection is it emulates a remote access as if what you're reading from is from a file. Of course, the server I've shown is busy handling one socket. A typical server uses parallelism and is able to have multi-threading. So typically, a server will consume one connection request. As soon as it accepts it, it forks a socket and serves that socket and returns and will consume another one and handle those in parallel. So typical TCP server must use some form of parallelism, which is typically in the form of threads here, to be able to serve a number of connections here. The UDP server might do the same as well, but the UDP server most of the time is expected to handle the process, the message very fast. Otherwise, most often we would use TCP here. A mental model of what the operating system does with TCP sockets. Here I have a non-connected, so with TCP I have an unconnected TCP socket here. As soon as the application program has accepted one SYN packet from that, it creates another socket, and it's up to the logic of the application program to activate a different part of the logic here. So the same application program typically will have multiple sockets here. All of those sockets are bound to the same local port. So, but now the operating system knows where to send the packet to. They're bound to the same local port, but they're not connected to the same remote destination. So packets that come here will go to different sockets that have the same local port. For example, an HTTP server that is bound to port 80 will have as many sockets open at a given point in time, all bound to port 80, but serving different clients. Voila, that's all for today. Thank you very much, and enjoy the rest.